Okay, so the direct solver. Okay, I'll give you some very quick tutorial of so the algorithm background, why we use a direct solver, and in particular, I will talk about sparse data structure because that's the algebraic interface to a lot of the solvers. And then I'll give you some examples. We'll show some hands-on. We'll have some hands-on exercise. So in the morning, you already heard from Barry about solving linear systems. So essentially, there are two big categories of solving the strategies of solving linear equations. One is the iterative methods, the Krylov method that Barry has in-depth this explanation in his talk. So the nice thing about this is the matrix A is not changed. It's read-only. So the majority of the work, the critical part of the Krylov method is to do the sparse matrix vector multiplication fast. And in fact, one of the advantages is since you only need a matrix vector multiplication in many cases, you can support a matrix free. So you don't need to have a matrix explicitly formed. So that's a very nice thing. And it's relatively easy to optimize and parallelize. In fact, if you go back to the literature, there are probably 100, 200 papers. And even now, when on the new architectures, there's still papers about how to do SPMV, sparse matrix vector multiplication on KNL, on GPU, et cetera, et cetera. So the direct methods, in contrast, one of the unpleasant things is matrix A is modified. It is factorized into L lower triangular matrix, upper triangular matrix, which you saw from Jack's talk this morning. And in the dense case, it's not a big deal. Your L and U, it's still fully populated, lower triangular, upper triangular. But in the sparse case, L and U, they have very different sparsity than A. So that's something very unpleasant. It's harder to optimize, parallelize. But the advantage of this method is numerically robust. So for very difficult problems, you will still be able to get solution. And the disadvantage is higher arithmetic complexity. And often the bridge between the two classes of methods is you use a direct method to precondition iterative methods, meaning that you solve a transformed linear system there where M inverse is your preconditioner. And very often, this preconditioner is built on top of direct method, factorization types of algorithm. So in this project, we have been working on two lines of code. One is SuperLU, which has a conventional direct solver for general linear systems. And another one is a more recent StrongPack, which I call inexact direct solver. I'll show you why it's inexact. And the widely used scenario for StrongPack is more like using as a preconditioner. So in SuperLU, in the direct, in the conventional solver, usually for 3D PDEs, you will get order of n square flops. This is already much smaller than order of n cube compared to dense. But still, it's not optimal, right? And the memory also, it's not optimal, not linear. And in this code, it's written in C. We have hybrid MPI plus OpenMP plus CUDA for GPU. And we do provide a Fortran interface and the real complex arithmetic. One of the nice things about a direct method is once you have a very good LU factorization, then after the solution, you can use this LU factor to estimate the component-wise error bound for your solution. So you get how good is your solution is. And then we can guarantee the solution with the iterative refinement. Also, you can use the LU factor to estimate the condition number of your linear system. And for StrongPack, we do something clever, look at the structure, low-rank structure of the matrix. So we knock down the flops to quasi-linear. It's not quite linear yet. And the memory is linear for many 3D elliptic PDE. So this one, it's a recent development. We started using C++, which is nice. So we can use a template to get all different data types. Also 32-bit, 64-bit integer very easily supported. And here we use MPI plus OpenMP. We haven't done GPU yet. Again, we have a Fortran interface, a real complex, et cetera. So the installation in the past, we did the traditional way. The user has to edit the make file to define the compiler optimization flag, etc. And the benefit of working on this ideas, recent DOE-funded project, and also the current ECP project, is we move towards more automatic installation process. So we have this CMake build system built up right now. And what you need to be careful is there are several dependencies. We depend on the BLAS, which Jack has talked about, and also the graph partitioning package for ordering, which I'll mention actually in the hands-on. We'll see how it affects performance. So once you get these dependencies, then you are ready to go. And the critical performance component is really this BLAS library. So in our distribution, there's a reference implementation of BLAS, but it's not very fast. So ideally, you do want to, if you have on a supercomputer like the one at NERSC or the Cooley, then your vendor usually provide a very fast BLAS library. Or you can use the open source library called OpenBLAS or Atlas. So you can Google those. So that's critical for performance. The reason is that internally we have, even though the global matrix is sparse, but internally we look at dense blocks and we try to apply BLAS operation GMM, level 3 BLAS on those dense blocks. And for GPU usage, for multi-core GPU, so in order to use OpenMP, it's relatively simple. You just set the environmental variable to however number of threads you want to use. To enable GPU, right now we only have support for NVIDIA GPU using CUDA programming. So you can still use the distributed GPU cluster, for example, the one machine at the Titan at Oak Ridge. We use MPI, and each node, multiple cores, you can use OpenMP, setting the OpenMP number of threads. And also, each node has a couple of GPUs, so you can add on this GPU functionality. So to enable this, when you compile the library, you need to set those environment variable before you compile. So that's set up in the make.inc. And in terms of performance, we did some testing on the 100 nodes GPU clusters. We see, depending on the sparse matrices, we see somewhere between 3 or 4 times better performance compared with without using GPU on those machines. So it's a sparse code, as in the panel, the panelists have discussed. It's not easy to have a good performance on GPU. And to be able to get 3 or 4 times speed up, it's already quite good. If you do the dense matrix like a magma library that Jack was talking about, you could probably, with a GPU, getting 20 or maybe sometimes 100%, 100 times speed up, et cetera. So that's a difference from dense. So talking about the algorithm a little bit, the direct solvers, one of the nice things is it can support a very wide range of applications. Here is a list of a number of them. And can work with the symmetric, non-symmetric matrices, indefinite problems, and very ill-conditioned problems. So the factorization essentially is not very sensitive to those numerical properties. And typical example of the matrices we are dealing with, the matrix A could be dimension of in the million. But every row, on average, probably has only 100 non-zeros. And when you increase the problem size, the dimension, the number of non-zeros per row usually doesn't increase. So that's the typical PDE discretization matrix property. And certainly, depending on the application, you could have looks very well-structured problem. And sometimes for the chemical engineering application here in this case, the sparsity pattern could be very irregular. So the code needs to be able to accommodate all these different structures. So then the first question is, what is the data structure you want to use? And very often we use some kind of compressed representation. In this picture, I show you the compressed row storage. So n is the dimension of the matrix. In this case, is 7 by 7. And the number of non-zeros is 19, only those non-zeros there. What you do is you store row by row. It's 1A, 2B, then CD, 3, etc. So it's by row. And then you have a column index corresponding to each non-zero. For example, for this F, the column index is 5. And then you have a row pointer pointed to the beginning of each row of this data structure. So it's the first row starts from the first entry. The second row starts from the third entry. The fourth row starts from the eighth entry, etc. So then the algorithm will work through this compressed data structure row by row. And then there are other different type of compressed structure which you can look up from this template for the solution of linear systems. There are a number of them. Depending on your algorithm, you may want to use row-wise, column-wise, etc. And what about a distributed matrix, sparse matrix? So in this case, for linear system, usually user only has the A matrix you need to input, and the right-hand side, B, could be one vector, could be multiple right-hand sides, a matrix. Usually it's a dense here. And internally, we factorize into L and U. And you don't need to worry about the data structure for LU because you only need to know what's the solution, right? So LU is a separate thing. So for the distributed input, what we do is we have 3 processors here. We partition the matrix A and B in the conforming block row format. Then for each sparse matrix, each local part, you need to do local distributed compressed row. So that's the data structure here. In addition to what you have in the sequential compressed row, what you have here is also some data structure to record the number of non-zero locally. For example, for processor 1 here, I have number of non-zero local, it's 7, and number of rows is 3, and the first row here for processor 1, it starts from 2. In the global matrix sense, it's 0, 1, 2, the second row. And the rest is the same as the 3 arrays, number of the non-zero values of my processors, the column index, and the row pointer, okay? So that's the distributed compressed row storage. Once you set it up on each processor, then you give to the code, then we'll know how to piece together this global information. Where is the partition boundary of the different pieces? And as I mentioned, that internally, you don't need to worry. It's LU factored matrices. And we use this 2D block cyclic layout that Jack has a detailed description early in the morning about the dense scalar pack. And we use the same thing. The reason is to have a load balance and also avoid unnecessary communication. But of course, it's very complicated for sparse matrices. You only store the non-zero blocks in this 2D block cyclic layout. So the only thing user needs to input is to set up this process grid. And you want to give the process grid as a square as possible. If it's not a power of 2, then you give a row dimension slightly smaller than column dimension. So 2 by 4 is better than 4 by 2. And 4 by 8 is better than 8 by 4, etc. So then let's see the algorithm, the 2 packages. So what happens in the sparse LU factorization, what's not very pleasant is this, the filling element. So to begin with, look at this cartoon. I have the number of non-zeros at this black dot here. But when you do Gaussian elimination, they will generate these red dots. That position originally is 0. But after the elimination step, after step 2 of elimination, because of this non-zero here, you will generate a non-zero here, which is flagged as red in this little cartoon. So you have a number of the red dots and filling elements generated. And that's not good in terms of performance. That's why the algorithm complexity is not order of n, it's not linear because of this generated filling elements. And the size of LU data structure will be bigger than A. How much bigger? It depends on the matrices. So depending on application, it's very hard to say. So usually it's for 2D problem is about a factor of 10. For 3D problem could be 50 or sometimes even over 100. So it's not very good there are different ways to organize the elimination. One is in SuperLU, we use the DAG-based approach, and in the strong pack, we use the multifrontal approach. Essentially, it's just a different way of when do you do the update of the Schur complement at each step. In the DAG-based approach, you update directly. In the multifrontal case, you organize as a tree, then your Schur complement update is accumulated along the tree. So the advantage of this is you use less memory, which is a good plus for direct solver. But in this case, you use more memory. But then you can imagine you have a relatively simpler graph to manipulate to do the task scheduling. So those are the different algorithms. So then from the algorithm point of view, because of this filling, then we have a lot of pre-processing steps in order to optimize performance. One is you can reorder the equations to minimize the fill, maximize the parallelism, this ordering phase, and also predict the filling positions. It's a symbolic factorization. Then you design the data structure for the LU, and that's another combinatorial phase. So all the pre-processing steps, it doesn't take too much time, but those are difficult to parallelize. And the numerical part is the factorization triangular solution. We spend a lot of time optimizing this, especially on newer architecture. So just from a user point of view, for efficiency and stability reason, we actually never factorize A itself. We do this pre-processing. So one pre-processing is equilibration, the multiply two diagonal matrices so that this balanced matrix will have lower condition number. And also we use the row permutation so that you get a large diagonal on the large elements on the diagonal. You have more stable factorization. And we use a column permutation, symmetrically permuted this transformed matrix so that you get a smaller number of fill in the LU factors. And if you turn off everything is null, you factorize A. Otherwise, by default, you factorize this matrix. And the performance tip is BLAST, as I mentioned, and then there's a environmental routine, which are several block sizes you can tune. And one of the XSDK for ECP project is to have an automatic tuning for this block size. So recently, we have done performance optimization on the Knights Landing machine. For a single node, we do a lot of vectorization, including vectorize the scatter operation for indirect addressing. So we get something like, for different matrices, get up to like 70% better. And then if you look at the strong scaling up to 32 nodes, then you get very good up to a certain point. Then what's the bottleneck is the communication, the lack of parallelism. So we are doing the 3D algorithm right now to reduce communication. So that part of the algorithm is not released yet. So then there are examples. So one of the examples I want to mention is you can divide the process grid into different subgrids, then do block Jacobi preconditioning. Remember, we were talking about preconditioning. You can set up multiple preconditioning steps for the global GMRES or any Krylov methods. So this example shows you how to set up the different process grid. So the strong packed inexact direct solver here, the idea is really look at the off-diagonal block. It's, the concept comes from fast multiple idea. So diagonal block near field, you do exact. Off-diagonal block, far field, you do approximate via low-rank compression. So that's this part, even though it looks like dense, but you use this SVD type of compression. That's lower your memory requirement, arithmetic, et cetera. And then you can see that for 3D Poisson, the direct solver is order n square. But for the strong pack, it's roughly quasi-linear, much lower. And then we have good performance number here. So I think we'll move on to the hands-on.
So we're on from the main lesson page, sparse direct solvers. And then go all the way up to the top level on the hands-on directory tree there. And then CD to MFEM. We're going to go back down. Examples, AppTest, SuperLU. Okay, so again, we're going to use MFEM as a demonstration vehicle for some of the features that Sherry was talking about in SuperLU in this case. We're we're using this application, convection diffusion, convift, that should say .cpp there. It's a C++ application, not C. And it's solving this differential equation, which involves a combination of diffusion and advection. Let's see, this is the advection term that has to do with velocity, and this is the diffusion term, I think. And this R represents, if you will, some dye, think of it as like some ink or some dye that's being put into the flow here. And so you can think the initial condition looks like this, where R represents this source of dye that's being dropped into this flow. And what this application is modeling is just flow to the right in the positive x direction. And the knob that you have on the application is say what the magnitude is of the velocity in the positive x direction. And this problem is known to cause iterative solvers a lot of grief as the velocity gets higher and higher. So again, as in other examples, you can get help with various of the arguments. Well, actually, you can't actually. My apologies. I'm sorry about that. What you do get is it prints out the actual options used. My apologies. Each time. In fact, all of these applications try to print out all the options used so you know what you actually ran. So the first thing is we'll just run a iterative solver, GMRes, with a velocity of 100 to the right.
So this is already preconditioned by the algebraic multigrid hyper that Eureka is going to talk about soon. So it's the GMRes preconditioned by hyper.
And so we just ran it. It turns out with the default arguments to convdiff, forget the minus help there. Basically, this is what it runs with, not using super LU, and in particular, velocity of 100. Okay. And the result, that if we plotted in Visit, and if we were doing live visualization, which I'd love to do, we could show you how to plot in Visit. So now let's do that same run, except we're going to increase the velocity to 1,000, but still use an iterative solver and see what happens. So it ran for many more iterations. I'm just displaying the last few here. There's an animation here as well. So first let me focus. This was the final result, the contours of the final result that it computed. All right. And what we're doing here in this movie, which I'll go ahead and run it, sorry. We're running this, but for starting at a velocity, we run the problem starting at a velocity of 100, and then increase the velocity in increments of 25. Keep doing this solve each time to see what we get. So eventually, you see it looks like it's kind of doing okay, and then the result finally just explodes. And the two plots below here are showing the residual on the right and the time dissolution. So what do you think's happening? Bottom line, the GMRes just can't deal with is it the condition number on the matrix?
Yeah.
Okay, so the condition number of the matrix is getting really bad. So now we're going to run it, except we're going to turn on super LU in default mode at 1,000. Now it'll take a little bit longer to run here, 20, maybe 25 seconds. And that's because it's doing a lot of is it doing reordering of the?
No, so the default is using the natural ordering, and the natural ordering is never good actually. So you will get a lot of field. So natural ordering from the 3D problem, it looks like a big band, right? The outside band and the middle band, etc. But when you do this elimination, you get field within the band. But what you will see that the next one, we will use any other ordering, even, for example, minimum degree ordering, matrices, graph partitioning ordering. You change the ordering of the equations and the variables, it's symmetric permutation, then you get a much smaller number of fields.
So it did finally run to conclusion, and what Sherry has is the super LU libraries pointing out.
So this quantity tells you the amount of memory needed to store the LU factor. This is LU is a field after the filling, okay? And that's the time. So we'll go to the next.
Okay,
so remember this is 41 here, megabytes for the LU.
And so that's
the
that's the
one.
computed, in fact, let me zoom in on that. That's the computed result for a velocity of 1,000 using Super LU. So the iterative solve was not even able to give us this result, and Super LU is giving it to us. So now,
So here I'm using the minimum degree ordering there.
so this argument SLU call perm 2 is changing the ordering to what algorithm, Sherry?
It's the minimum degree ordering. If you are interested, I can show you offline how this different ordering algorithm works. So you can see now the LU megabytes is reduced by fourfold, from 41 to 10, right? And the time is significantly shortened, from 30 seconds to like 1 second.
30 times faster, just by changing that parameter within Super LU. Let's see, now we're going to...
So that's another ordering, the graph partitioning type of ordering, metis.
So this is using metis internally to do this.
Right,
yeah.
so it's still the option here is 4, it's using the metis.
So we'll rerun that.
So now it's improved a little. It's from 10 megabytes to 9 something, and the time is also improved a little. So this is actually a relatively small problem. Minimum degree is still very competitive with metis. Once you blow up the problem even further, then usually metis, graph partitioning, metis Scotch is much better than minimum degree.
And so what we're plotting here is that same problem. We're starting at velocity of 100 and then increasing to 1,000 in increments of 25 and letting Super LU with the call perm, the metis ordering, to solve this problem. So we solve all those, animate that, and see what it looks like. And then this is actually just the time that each of the run took. So you can see it varies, but actually not by a whole lot there. Sorry, this looks, in fact, I don't know if we can zoom in on that and get slightly improved. Yeah, from 0.4 to 1.6 seconds. So I think that's the last exercise in this one.
Okay, so then there's
oh, no, there is.
There's
okay.
one more
so we're
MPI, right?
Right.
Yeah.
So thank you. Sorry, I forgot. So now we're going to do a 16 processor run. And what we're going to do is just kind of grep the output here after it runs. Oops, sorry. I don't have this variable defined.
Okay, probably you
apologies.
can just look at the screen here.
Okay, so my apologies. I don't have this variable defined and resolving that at this point. So what we've done is we've done the run, put all the output into a file, and then we just grepped for the two numbers, the time to solution and then the residual. And you can see the variation in times here from, maybe what, 7 seconds, was 9 seconds I think was the fastest MPI rank, and maybe around 20 the slowest up there. And just to comment, we did increase the problem size. This refine basically increases the problem size by a factor of 16, and then we ran it on 16 processors.
So the 16 is the number of non-zero, dimension of the matrix increased by 16. But as I mentioned, the operation count is usually n squared. So the number of operations, flop count, is roughly 256 times more. But remember, then the time, we're running on 16 processors. So the time is actually, it's roughly divided by 16, right?
These times are approximately 16 times the time for it to run that number, approximately.
Yeah, so it's roughly for 16 processors, you get about 16 speed up, So it's for a small number of processors, it's not a problem. Any questions?
You had said that it was a symmetric permutation. What is that?
The purpose of symmetric permutation is I want to keep the diagonal element still on the diagonal.
Same how for the LU decomposition, you need to do a lot of pivoting and build a DAG graph.
That's right.
Doesn't seem very ideal to be porting it to the GPU. It's
Yeah.
like a more CPU-based.
That's a very good question. So for our GPU implementation, all this permutation graph pre-processing step is on CPU. What we do is for each numerical factorization step, we do the short complement update, which has big N steps. Each step we do that on the GPU. At the same time, we do the little panel factorization on the CPU. So it's simultaneously both happening, then they handshake to exchange some data.
Would you say that the LU decomposition is ever a good choice for the GPUs as opposed to QR. I feel like QR would run better.
QR has more filling even. You know, in the QR R factor Q matrix, they have more filling in the sense that you get a denser matrix. It's better on GPU, but on the other hand, for sparse QR, you get even more. You know, so the complex it will be slower overall operation count. Yeah.